We think of a spin 1/2 as a polarized quantity, like a bar magnet pointing up or down. Here we find spin displays wave-particle duality. In free flight, it acts like a wave, and when measured, it acts like a particle. A spin is similar to a photon in free flight. It is a wave, and upon encountering a field, it acts like a particle. Formulating the wave nature of spin 1/2 is a new feature of this work. It shows the wave nature of a spin is actually spinning of the axis due to a quaternion, like the helicity of a photon. It has two axes of spin polarization perpendicular to the direction of linear momentum, analogous to the electric and magnetic components of a photon. These two spin around their axes. In free flight, these two spin axes of 1/2 couple to give a spin of magnitude 1, again like a photon, which has a spin 1 as well. Even more, I will show that this spin 1 has only plus or minus 1 components, and with no 0 components, again like a photon. Upon encountering a field, the particle nature emerges. Like emission and absorption of the energy by a photon, so a spin 1/2 displays similar behavior after the two magnetic states are split by the Zeeman effect. When a free flight spin encounters a field or filter, the wave nature stops, and the spin evolves into the usual spin 1/2 that we observe. It is this transition from wave to particle that is responsible for the violation of Bell's inequalities. The mechanism for this violation is how that free flight spin of 1 decouples into the usual spin 1/2 we observe. This is far from the usual explanation that declares the process is due to non-locality and its associated quantum weirdness. Only one type of experiment that is used to assert that nature is non-local, and that is the coincidence EPR experiment shown here. Starting in an entangled singlet state at the source, upon separation each particle moves towards the filters of Alice and Bob. I will not go into the details of these coincident experiments here, but the results seem to suggest that entanglement is maintained even after the two separate. We call these two particles EPR pairs. We know that all particles interact with some inverse power law, which dictates that upon leaving the singlet state, the entanglement should be lost. When the two spins are beyond the range of internal couplings, the entangled state changes to a product state. Upon separation, they will no longer be entangled. The great surprise is that this does not seem to happen. Rather, the experiments display the same correlation as before they separated. This is one statement of the EPR paradox. How is the entanglement maintained over space-time? Must we accept they remain entangled and forgo locality? Here we suggest a way to maintain locality, yet still account for the experimental observations without any non-local connectivity. But this goes against the current view, which is almost universally accepted. Using a singlet state, the correlation from quantum mechanics gives this minus cosine term. The angles of theta A and theta B are the filter settings that are randomly set by Alice and Bob. The correlation is plotted here as a function of the difference between those settings. If we assume Einstein locality, then upon separation, the product state gives a product of two cosines of these angles. The main usefulness of Bell's inequalities is they allow us to quantify the correlations from the CHSH form of the Bell's inequalities, that is, after Clauser, Horn, Shermoni, and Holt. Bell showed that the classical CHSH correlation should never exceed the value of 2. Indeed, the product state obeys this rule, but the experimental evidence from coincidence experiments violates the CHSH inequality because the correlation from the entangled state is 2 root 2, or 2.828, as shown here, and that is what is observed. Here is a view and summary of the correlations in this figure. At various settings between Alice and Bob, the correlation from an entangled state of an EPR pair at the source is the same as after they separate. The data comes from EPR coincidence experiments. The triangle results from dropping the entanglement, giving the product state, and the difference, I call the mustache function, is the part that gives the violation of Bell's inequalities. It is this contribution to the correlations with a CHSH value of 0.828 that we must understand. At this stage, however, Bell's theorem is invoked, which is a general statement as to what is required to account for this difference. In Bell's words, if a hidden variable theory is local, it will not agree with quantum mechanics, and if it agrees with quantum mechanics, it will not be local. In proving this theorem, Bell asserts this difference can only be accounted for by non-local connectivity between Alice and Bob. Bell said they are due to non-local hidden variables, which cannot be specified. Despite this difficulty in grasping such a concept, today this is almost universally accepted. I point out again, in the treatment I present, there are no hidden variables. Spin has another property which has been missed, and that property is purely quantum mechanical and is quantum coherence. In this slide, I summarize the results of the correlation given by the entangled state of minus cosine, with a CHSH value of 2 root 2, to the product state with no entanglement, with a CHSH value of 2, and their difference, the mustache. The mustache must be the part that accounts for the entanglement. To me, this difference is due to a property that must have the form of minus sine sine, and when added to the cos term, gives the observed cosine term for the correlation. The missing correlation in the mustache function is due to a hitherto missed property of spin, the quantum coherence, which gives the wave-like behavior of a spin. It is measured as the helicity. However, explaining the mustache function requires a fundamental rethinking of how we view a spin of 1/2. This fundamental change requires understanding coherence, that is, the wave nature, and its relationship to the polarizations, its particle nature. These two complementary properties are contained in the singlet state. Polarizations are even states of plus plus or minus minus, and coherences are odd states like plus minus or minus plus. These are not displayed in the singlet wave function, so express this as a state operator by taking the outer product to give this matrix. The polarizations are the diagonal elements of this matrix, and the coherences are the off-diagonal elements. I call this a state operator, and not a density operator, because the singlet state is a pure state, and therefore so is the outer product. A density operator also can account for mixed states, but we are interested in one EPR pair of two particles that separate from the entangled source. Later, we will look at the correlation as a mixture of many different EPR pairs that are filtered under the same filter settings of theta A minus theta B. But for now, this state operator nicely displays both the diagonal polarization states and the off-diagonal coherent states. It is not necessary to deal with matrices. This singlet state operator can be written as the tensor product between the two identities of Alice and Bob, and the dot product between their two Pauli spin vectors. Now, the point I want to make at this stage is that if those two -1 off-diagonal terms are dropped, then we get the product state. Therefore, one can surmise that the mustache contribution that causes the violation of Bell's inequalities must be due to those off-diagonal coherence terms. This leads us to the starting point of the theory I am presenting. In calculating the EPR correlation of minus cosine and the product state, cosine-cosine, we always encounter a dyadic for both Alice and Bob. This is expressed using geometric algebra in the form here, which you can find in Wikipedia under Pauli matrices. It says that the components of a dyadic, I and j, can be expressed as a sum of two different terms. The diagonal elements of I equal j, and the off-diagonal terms of I not equal to j. The two terms are complementary because I cannot simultaneously be equal and not equal to j. The two are different contributions, with the first being totally symmetric and the second being totally antisymmetric. The first term describes polarizations and the second term describes coherences. This equation expresses the particle-wave duality of a spin, but it seems everyone neglects the second term because we can only measure polarizations. If it is included, as I will show, then the mustache function is due to the second term. Note also that the antisymmetric term requires a bivector, and this is shown here, which comes up in the commutation relations of the Pauli matrices. This bivector is critical to the properties of spin. However, the Dirac equation has no bivector and describes only polarizations. The antisymmetry requires the use of epsilon, which is a third-rank, totally antisymmetric Cartesian tensor called the Levi-Civita tensor. It is defined here and requires all components, ijk, to be different. It is easy to show that they give the vector cross product. Again, in Wikipedia, if the dyadic of the two Pauli spin vectors is contracted into the two filter settings of A and B, then we get two terms, the dot and the cross product. The dot product gives us the cosine theta A minus theta B, the term we have already found, while the second term gives the cross product. We must include both terms. Here, I is a 2 by 2 identity matrix. Recall this expression is valid for the same spin. If this is Alice's dyadic, then Bob has his own dyadic. The first term of this expression gives the symmetric contribution and leads to polarization we can measure. The second term has not been treated in the same way. It has been missed. Define then helicity as the antisymmetric and anti-Hermitian operator in terms of a bivector. I call it the hyper-helicity because it is defined differently from the usual helicity, which is the projection of the spin 1/2 vector onto the axis of linear momentum. The hyper-helicity generates the helicity, and the projected form in Minkowski space is its measure. The correlation from this term for Alice and Bob is calculated in exactly the same way that gives the product state for the polarization, that is, the minus cosine theta A cosine theta B term. So the hyperhelicity, let's call it helicity for short, gives exactly what we need, a product of two signs. It appears this operator is an element of reality of spin. It is complementary to the polarizations. I will not go into the quantum field theory at this point, but rather summarize the findings. First, as earlier noted, there is no bivector in the Dirac equation, but we need one. Now, the Dirac field has 4 dimensions in spacetime, time and 3 spatial components. It is represented by the 4 gamma matrices. When Dirac found his equation, he expected only 2 states of a spin 1/2, as is measured. But what about the other 2 dimensions? They also describe a 2-state spin, but opposite from the Dirac spin, its mirror image. Dirac interpreted this to be the antimatter twin of the measured spin. The current view of these two spins being a matter-antimatter pair is accepted and has been around for almost 100 years. It leads to antimatter production, the sea of electron model, and hole theory. I will not detail the properties of the gamma matrices except to say that they still anticommute. This is a requirement to conserve mass and energy from the Klein-Gordon equation. If I multiply one by I, they still anticommute. Introducing a bivector changes the symmetry of the two-dimensional Dirac equation from the usual SU2 to being a normal subgroup of the quaternion group, Q8. Call this set of spin components the quaternion spin or Q-spin. It gives a spin 1/2 structure with two axes of spin polarization and the bivector, which orients the 2D polarization plane in 3D space. This is the origin of the spin structure that is like a photon, two axes of spin, sigma 3 and sigma 1, and the bivector, I sigma 2. The resulting equation, modified from the Dirac equation, can be called the quaternion equation. It is non-Hermitian, but it separates nicely. It separates spin spacetime into two distinct spaces. In free flight, the 1 and 3 axes are indistinguishable, but the bivector is not. Permutation by a parity operator, P13, does not change the 1 and 3 dependence of the Dirac equation, but the bivector is antisymmetric to this permutation. This leads to a non-Hermitian Dirac equation, and the solutions are mirror states, just like Dirac found. These mirror states are reflected under the permutation of the 1 and 3 axes. The mirror states are in a right and left-handed coordinate frame. However, we can add and subtract the two mirror states, and this leads to the separation of spacetime into two parts, one for the spin polarization, and the other for its complementary property, the helicity. Note the gamma matrices now have a subscript S, which denotes spin spacetime. Each structured particle can be oriented differently, and each needs its own body-fixed frame. We do not need a spin spacetime for a point particle, but we do for a structured particle. Let me summarize. Introducing the bivector leads to a non-Hermitian equation with two solutions that are mirror images. They are reflective states with no fixed parity. However, this non-Hermitian equation separates into two equations of even and odd parity, which are sums and differences of the mirror states. The odd parity states describe the spinning axis driven by the bivector I sigma 2. The even parity states exist in a two-dimensional spin spacetime, which is projected onto Minkowski spacetime. The solution of the Weil equation is a unit quaternion, and this spins the axis of linear momentum. That is all it does. It spins the plane and averages the polarization. In free flight, spin displays no net polarization. That is its wave nature. In free flight, there is no polarization. In a field, the helicity stops and the polarization is manifest. That is its particle nature. Since spin has structure, each can be oriented differently, so that each spin is defined in its own body-fixed frame. This is oriented relative to Minkowski spacetime by a rotation. The spin spacetime diagram here displays the relationship between Minkowski spacetime and spin spacetime. Spin spacetime breaks up into two spaces, the two-dimensional plane of polarization of even parity states, and the S3 hypersphere for the quaternions that spin the axis of odd parity states. Now, in spacetime, we often talk about a world line that particles follow in Minkowski spacetime. Leonard Susskind, referring to a string theory, defined a world sheet representing a string's dimension. This plane is the possible world sheet of q-spin. Since the gravity of a tiny spin is negligible, Minkowski spacetime is flat. The anti-emission space of quaternions is not in our spacetime, but in the fourth-dimensional hypersphere S3. We cannot see it all. All we can see is the stereographic projection of the spinning 2D plane. We cannot observe the full quaternion space, but this treatment shows that nature extends beyond our dimensions. The spinning is generated from the hypersphere. The body-fixed frame of the 2D spin has unit vectors in the E1 and E3 body-fixed frame. The laboratory fixed frame in Minkowski spacetime is XYZ. Take the linear momentum perpendicular to the axis of linear momentum, so then E2 is equal to Y, and this is the axis that spins. Next, I discuss the 2D Dirac equation. The two orthogonal spin axes are mirror states. As mirror states, they must reflect each other, so they are shown precessing oppositely to maintain their reflective property. The two mirror states of one-half spin lie along the E3 and the E1 axes and couple to give a completely resonant spin of magnitude 1. This is also like a photon. Even more so, there is no zero component of this spin. The two axes spinning oppositely generate a spin component of, let's say, m plus 1. Reversing both gives the component of m minus 1. But to form the m equals 0 component would violate the mirror property, so it does not form. Note that a photon also has no m equals 0 component. Going back to expressing the spin dyadic in terms of the polarization and coherence, changes spin from always being in a polarized state of sigma to also having its complementary coherent term expressed by the bivector. Capital sigma denotes each spin axis as a q-spin. In this line, the expectation values are given, which are simple to work out. The result is in the body-fixed frame and gives the phase of pi over 4. Often properties are clearer from the body-fixed frame. Now, using the polarizations as a sum of the mirror states means this resonant spin is a sum of the 1,3 axes and normalized by a root 2. This forms the resonant spin of 1 by the vector coupling of the two spins of 1/2. The two axes are shifted by pi over 4. I'll come back to this on the next slide. Here I want to point out that the mirror states precess oppositely, and they are in phase, dictated by their mirror symmetry. In the quantum field theory treatment, which follows from the Dirac-Seev electron model, we get two equal but opposite energies. Again, following Dirac, these are treated as the matter-antimatter twins, so there is still a problem with the negative energy of the second term. Here, the q-spin interpretation is two axes spinning on the same particle, so there is no problem with the negative energies. The positive and negative energies of the two axes are just balancing each other. Quaternion spin appears to solve the negative energy problem of the Dirac equation. Look at this from the body-fixed frame and note that the resonant spin of 1 has two parts that are shifted by pi over 4. E3 is rotated to the right by pi over 4 and E1 to the left, so they lie on top of each other and form the spin of 1. If the signs of the resonant spin are permuted, we get 4 possible resonant spins as the bisectors of the body-fixed frame. In free flight, only the resonant spin is present. The two axes are superposed. Recall again that the resonant spin is averaged to zero by the helicity, but nonetheless the two spins of one half couple in free flight as it moves towards the filter. Here is a head-on view of a photon in free flight. The electric and magnetic components have the same resonant structure as Q-spin, and its helicity spins the axis perpendicular to this plane. Since experiments are done in the laboratory fixed frame, I must transform from the body fixed frame to the laboratory fixed frame using these relationships. Recall that E2 is equal to Y, so the filters and the spin plane are coplanar. Note also that the filter direction is included, as the contraction with A. The field and the spin are rotated from each other by the angles theta and theta A as seen in the transformation. It is easy to work out the dot products between the field and the E1 and E3 vectors, and with a bit of algebra we get the final result. The first line is an exponential quaternion, and since quaternions form products, it can be written as a geometric factor and a field quaternion. They are both unit quaternions. The second line writes this to display the two axes. After transformation, the first term is the E3 axis as viewed from the laboratory fixed frame, while the second term is the E1 axis as viewed from the laboratory fixed frame. These depend upon the local variable theta, which orients the spin in the laboratory fixed frame. These laboratory fixed frame equations are the most important here, and all the results and the simulation that follow depend upon this equation. Now consider the separation of an EPR pair and their correlation. The correlation is due to their common starting point at the source. Alice moves right in a right-handed frame, and Bob moves left in a left-handed frame. They leave the source in their common body fixed frames with common vectors of E3 and E1, but opposite values of E2, which is equal to Y, which is the axis of linear momentum. As an EPR pair, Alice and Bob share the same body fixed frame. If Alice is oriented by angle theta to the laboratory fixed frame, then Bob must be oriented by theta plus pi to conserve spin angular momentum. This EPR pair is rotated from the laboratory fixed frame by angle theta, but every pair can be oriented differently at the source. They are correlated by the product of their quaternion spins, sigma A and sigma B. The first term has positive helicity for Alice and negative for Bob. The second term is the opposite case, with a negative helicity for Alice and positive for Bob. We must include both cases because every EPR pair must be counted, and so we need both right-left and left-right helicity contributions as shown. As they move oppositely, they conserve linear momentum, they have the opposite resonance spins, so they conserve angular momentum. They spin the same way to maintain conservation of spin along their trajectories until they reach their respective filters. The correlation is defined as the product of the two spins, and each is contracted with their filters. Note that Alice is in a right-handed coordinate frame with a right-handed rule, and Bob is in a left-handed frame with a left-handed rule. Even though these two spins precess in the same direction, Bob has opposite helicity when viewed from the right-handed frame. Here is the earlier result, which is now used in the correlation expressions. Plug in the values which are written here. To calculate the correlations, note that Alice and Bob's orientation must differ by pi, as we just showed. Here we have the plus pi over 2 for Alice and the minus pi over 2 for Bob. These combine to give a phase of pi between the two, which gives the required minus sign in the correlation. Note that the common angle theta cancels, and the final result gives the desired quantum correlation of minus cosine theta A minus theta B. This is the same result as from quantum mechanics. In my paper on helicity, I showed that the correlation in the original singlet before separation, that is minus cosine theta A minus theta B, is conserved after separation from the two contributions of polarization and coherence. The reason I have the same correlation from before and after separation is an example of the conservation of geometric correlation. We have no entanglement and no hidden variables. There is no non-locality. This is from a product state. The difference is simply that we have included the antisymmetric part of spin. In free flight, the filter vectors must be removed, and this leads to a correlation of -1 throughout their trajectories until they reach the filter. This is reasonable. Spin decoupling is a common phenomenon. Think of Russell-Saunders coupling. Spins remain coupled so long as the spin-spin coupling is stronger than the externally applied field. In the EPR case, the coupling also depends upon the orientation of the approaching spin relative to the field. If the spin approaches the filter so that the field vector A is close to either the E3 axis or the E1 axis of the Q spin, it will decouple easily, and that spin will line up with the field. Its partner spins perpendicular and is so averaged to 0. In these cases, the resonance spin is destroyed. There is no coherent term in the polarized spin. It becomes polarized into the two-state spin we measure, and that is the usual Dirac spin. Note the positions on the correlation curve where there is no coherence, and these are when theta A minus theta B are close to 0, pi over 2, pi, and 3 pi over 2. I will soon show these make sense. If the spin approaches the filter so that the field vector A is close to the resonance spin of magnitude 1, it will not so easily decouple. Then the resonance spin persists and gives extra correlation from the coherence. This happens at multiples of pi over 4 on the figure. Suppose that Bob's spin is oriented relative to his filter, so that one of his spins lines up easily. This destroys his resonance spin, and the axis lines up, giving the usual Dirac spin of two states. When this happens, only the scalar part of the quaternion survives, as seen here. For this to happen, it is necessary that the difference between the filter angles and the one-spin axis is small, so the cosine is large. This is the condition for decoupling. Now, when the correlation is calculated in the same way as just done, the result is a product state, even though Alice's spin is still a Q spin. Here we show the result. Depending upon these orientations, we can get various product states, but no minus cosine term, which is found for the full correlation. There are 4 cases giving 4 types of coincidences when the filters at Alice and Bob are set, so they encounter polarizations and/or coherent spins. They are polarization, polarization, polarization coherent, coherent polarization, and coherent coherent. That means that only 1/4 of the coincidences give the full correlation, that is, the coherent coherent terms. Shown here, however, is a coherent polarized case. The previous slide showed the coherence coherence, which gave the full minus cosine term. With this, we can understand the filter settings in the CHSH inequality that give the maximum correlation and violation of Bell's inequalities. This occurs when the filters at both Alice and Bob are such that both favor Q spins over the polarized spins. These lie along the bisectors of the quadrants in the body-fixed frame. Let us set the angles of Alice and Bob anywhere so that when the spin orientation changes via theta, the filters will encounter the spins. Here is an example. However, we need both Alice and Bob spins to encounter a coherent spin at the same time. Otherwise, we do not get the full correlation and only a product state. If we choose the relative settings of theta AB to be multiples of pi over 4, then we can be sure that when Alice encounters a region of coherent Q-spin, then so will Bob. The most favorable settings are for the pi over 4 wedge shown here, which lies between 22.5 and 67.5 degrees on either side of the resonance simultaneously at Alice and Bob's filters. This happens over 2 pi. Under these conditions, as the body fixed frame orientation is rotated with the filters so set, then when Alice's coherent axis aligns with the filter, then so must Bob's. We get a maximum correlation for the CHSH inequality with these settings. There are 4 experiments here with A1, let's say Alice's filter, coupling with Bob's C or D settings. Likewise, A3, let's say again Alice's setting, is coupling with Bob's minus C and D settings. All 4 positions sample coherent spin at both filters. So the CHSH equation represents 4 experiments, each separated by pi over 4. Now any one of these filter settings, with Alice and Bob always pi over 4 apart, will sample different features of the spins. That is, either both coherent or polarized spins and different combinations, as they vary theta and rotate under the field. Putting in the values of these into the CHSH equation, that is, A1 dotted into D and C, and A3 dotted into D and minus C, gives a value of 2 root 2. Let's look at the first experiment. The upper cone is a fixed experiment under which the polarization can rotate. Rotate the spins in steps of 22.5 degrees, so that gives us 16 positions. We can see then how Alice and Bob sample the 4 cases of polarization, polarization, polarization and coherence, coherence and polarization, or both coherence. With A1 forming a pi over 4 wedge with either plus D or plus C, and A3 forming a wedge with either plus D and minus C, will give 4 experiments which will sample the coherent spins and the polarized spins in the same way. If the opposite quadrants are considered, then the 4 equations give the same results as the last slide, with a CHSH value of 2 root 2. Any pi over 4 wedge gives the same result, each contributing a cosine of pi over 4 and a value of 1 over root 2 for each. In the CHSH expression, changing the opposite quadrants give the same results. Let's go through the different positions slowly. One is polarization and the other is coherence, so a product state is formed. Now both Alice and Bob sample a coherent spin, so this gives a coherent state. Again, we have a coherent polarization, and this gives a product state, a product state, a product state, a coherent state, a product state, a product state, a product, a coherent state, a product state, a product state, a product state, a coherent state, a product state, a product state. Now we are back to the start. 1/4 of the coincidences will be coherence-coherence, giving the coherence correlation, and 3/4 will be polarization product states. Here is more justification of the results of the last slide, that for filter settings of pi over 4, the correlation from coherence is maximized. This depends upon the boson spin from both Alice and Bob being sampled simultaneously, which is within the pi/4 wedge. Note that quantum mechanics tells us that a spin vector makes an angle with respect to the filter orientation and precesses about it. This is the formula in terms of the magnetic quantum number m and the spin quantum number s. For a spin 1/2, the angle is given by 54.73 degrees, which is also called the magic angle. A boson spin of 1 makes an angle of chi of 45 degrees. At this angle, the precessing bosons have maximum correlation of -1/√2. Any other orientation of Alice and Bob's filters that must be within that pi/4 wedge will give less correlation. The pi/4 precession angle gives confirmation that the bosons are spinning and not the fermions. The reason for the violation of Bell's inequalities is then due to the resonant spin at settings of pi/4, which are sampled simultaneously by Alice and Bob. At multiples of pi/2, the correlation is only from the product states. Turn now to the simulation. The correlation must distinguish between polarized states and coherent states. Here is the result written from before, and it expresses the two axes of the quaternion spin in the laboratory fixed frame. From the figure, a coherent spin has both axes coupled to the resonant spin, but the polarization states have only one, either E1 or E3. Here are some possible filter settings. Either Alice or Bob's filter is close to the E3 spin axis, this is Dirac spin, with its E1 twin averaged leaving only one axis, or either Alice or Bob's filter is close to the E1 spin. This again is a Dirac spin, but with the E3 twin averaged, leaving only one axis. If the filter is close to the resonant spin, two axes are involved. In the first two cases, we need only know if the axis is spinning left or right to know if the click is a plus or a minus. For the resonant spin, we have two situations. Either the filter is offset so that E3 is closer, then we assume that axis will align with the field after the resonant spin has decoupled. If E1 is closer, then that axis will eventually align after decoupling. It is unlikely that the filter can pass the resonant spin intact without it decoupling, so we dismiss that case. For a Bob, as long as he is in the pi/4 wedge, one of his axes will align, but not necessarily the same axis as Alice's. If Bob's spin is not in the pi/4 wedge, then it will be polarized and will only get a product state. Since these two axes spin oppositely, they have opposite spin, so it is important to know which axis lines up when the resonant spin decouples. The algorithm for the simulation is to distinguish between polarization and coherence, which means dealing with the alignment of either one axis for polarization or deciding between the two axes for coherence. In the case of one axis, we simply then decide which way it spins by finding out if that axis is positive or negative, with a plus click for positive and a minus click for negative. For this, we use the imaginary part of the spin axis. For coherences, we decide on which will align by taking the larger of the real parts of the two axes and then deciding if its imaginary part is positive or negative for a plus or minus click. Note that the filter angle is doubled when choosing the larger real part because the Larmor precession of the coherent spin is double that of the polarized spin. If we do not do this doubling, then the simulation fails. However, To decide if the imaginary part is positive or negative, we revert to the Larmor precession of the spin 1/2 without the doubling, because at that stage of the filtering, the resonance spin has already decoupled and the spin is polarized. This is what the simulation program does. It treats one axis for polarizations and two axes for coherences, and then decide which way they spin. The simulation of the correlation must distinguish between polarized states and coherent states. Here is the result. The two single axes for polarization simulate the product state with a CHSH value of 2. Actually, the simulation finds a CHSH value of 2.027. This is of interest because the product state for polarization simulates a small violation of Bell's inequalities, thereby violating his theorem. The single-coupled axis for the coherent state gives the mustache function with a CHSH value of 0.968, or almost 1. The sum of the two give the full correlation of 2.995, and that is almost 3. There is more correlation in the simulation than from quantum mechanics, which gives 2.828, 2, and 0.828. The CHSH value of 2 is the boundary between the classical polarizations and the quantum coherences. Quantum mechanics and quaternion spin both give values of a CHSH value of 2.828. The simulation gives a correlation of almost 3. This leads to the question, as does nature have a value of 2.828 or 3? Experimental correlation is determined by counting the clicks from the equal coincidences, that is plus plus and minus minus, and the unequal coincidences, that is plus minus and minus plus. The correlation is the difference between the even and odd clicks divided by the total. Note that the total number of clicks is unimportant because the more clicks just improves the accuracy but does not change its value. We define the polarization and coherence correlation in the same way. We obtain the full correlation by adding these two contributions. In this section, that is justified. Normally, 2 or more contributions to an observable are added, but each is weighted by its probability. In this case, there is a difference between the two processes because they are complementary, which means that the n equal and the n non-equal clicks are distributed between the polarization clicks or the coherent clicks, not between the polarization clicks and coherence clicks. It is one or the other. If we use this formula for A equal to the polarization correlation and B equal to the coherence correlation, then this expression cannot violate Bell's inequalities. Take, for example, an equal number of polarization and coherence clicks. So the probabilities of PA and PB are both 1/2. It is easy to see that the total correlation would be equal to half of the observed, which is the sum. Complementarity resolves this. We talk about observables A, B, and C and their algebra. In this case, C is a mixed state, and A and B are pure states. Pure states are extremal points on a convex set, and interior points are mixed states, so that C is a weighted sum of 2 pure states. In our case, both polarization and coherence are complementary properties, and both contribute to the correlation, click by click, sometimes polarization and sometimes coherence. In the first case, complementarity is not included because both A and B simultaneously contribute. To include complementarity, we must introduce two Boolean operators defined that if delta P equals 1, then delta C equals 0, and vice versa. Including this, the pure polarization contributions and the pure coherence contributions are now exclusive of each other. Rather than having an experimental point as a weighted sum, now the experimentally observed correlation is defined as two exclusive contributions, that is, either polarization or coherence. Recall that the fundamental reason for complementarity lies in the geometric product of the Pauli matrices, which have two exclusive contributions. The first is symmetric and the second is antisymmetric, and only one can occur at any instance. We therefore conclude that for complementary properties, we must write the sum using both the probabilities, which give the distribution of cliques, and the Boolean operators to ensure complementarity. On this slide, we showed that this leads to the sum of two contributions without the weighting due to the probabilities. Note that the total number of cliques must be distributed between polarizations and coherences, so that the total number of polarization cliques is P sub P times N total, and for coherence cliques it is P sub C times N total. Substitution of these values into the complementary expression shows that the experimental correlation is the sum and not the weighted sum of the two parts. Therefore, the total correlation agrees with the experimental accumulation of coincidences. Ideally, a filter would show this to be true. A filter could be built by polarizing the source so that all the particles in the beam are oriented at a fixed value of theta. Then the filter angles can be chosen to favor polarization cliques or coherence cliques. Here we point out some of the features of the simulation that give a CHSH value of 3 rather than the 2√2 from quantum mechanics. First, the coherence can be nicely fit into two opposing sine functions. This fits the simulation better than the quantum term. There is a 1/4 prefactor in this function, and this is a consequence of only 1/4 of the coincidences being from coherence terms. Note the doubling of the filter angle for this is required to fit the data, confirming the doubling of the Larmor frequency for the resonance spin. The CH value of 3 comes from the values of the correlation, which from the simulations are at pi over 4, 0.746, and at 3 pi over 4, at 0.758. These converge to 3/4, so giving a 1/4 of the coherence and a 1/2 from polarization, and this is in a ratio of 1 to 2 for the coherence to polarization, therefore supporting a CHS value of 1 per axis. Quantum mechanics and Q-spin give the same minus cosine for the correlation, and both give a violation of 2√2. That is because they both start from the same singlet state, and correlation cannot be destroyed in the separation. This is an example of the conservation of geometric correlation that I talked about in the second paper on hyper-helicity. So my Q-spin only gives the mechanism of how the correlation is conserved after separation without non-locality. I cannot get more correlation than there is in the singlet. Now I want to point out that the singlet state is an approximation, and there is more correlation available than from using the entangled singlet state. That is why the simulation gives 3 and not 2√2. First, the singlet is up-down, anti-symmetrized, fermionic, polarized state with net zero angular momentum. This is the usual way it is written and what everybody uses. This is a possible view of the singlet and how it might evolve and separate. Q-spin has structure and helicity. Think of the electron. The magnetic attractions here are balanced by the repulsion of the charges. They spin about the axis as shown. When they separate, they do so while conserving everything, and everything settles into their separate trajectories, spinning the same way and forming a resonant spin that goes on to Alice and Bob for filtering. I like to think that the intermediate axis theorem works here as they settle down into their free flight forms. A long time ago, in 2007, I showed that it is possible to separate the Bell states into products, but you must use Q-spin. Back then I called it the spin fringe. And here it is. If you plug in all the Pauli spin matrices, they add up to the singlet. That is 8 terms. Note that Alice and Bob have opposite polarizations and the same helicity, which is consistent with how they separate. Here is one of the 8 terms, and you can see the tensor product forms a 4-dimensional component of the Dirac field of Q-spin. This is not Hermitian. Changing N3 from +1 to -1 for Alice and Bob just flips the polarized states from down to up. The off-diagonal elements are the coherence terms, and these tensor products give this line of 4 contributions. 1 is the polarization, and 3 are coherent terms. Note that there are now 2 terms that are not in the final singlet state. These terms cancel when the product states are summed to give the singlet state. All 8 terms are variations of this, and the tensor products always give a row or a column of these numbers. All have common outermost matrix elements that are not 0. The final singlet, of course, does not have these terms. It is useful to work them all out, and you can see how things add, combine, and make sense. This is not difficult. The left block here has Alice polarized plus and Bob minus. The right block is Alice's polarized minus and Bob plus. These 4 add to -4, and these 4 add to -4 also to give the 2 coherent terms in the singlet state. Now add the diagonal terms that give +4 for each one of those 2 diagonals shown. There are 4 components. Those 4 components are the usual singlet state. All the other terms cancel, like this set and that set, etc. So there is a cancellation of correlation when the products are added. This means the correlation in the parts is greater than in the sum. Note how these terms all have the same polarization, but change the helicities, and all cases are covered. Now let's take the tensor product to give the 8 product states. These are the 8 ways an EPR pair can leave the source. They do not leave the source in an entangled state. Although each part of a pair is non-Hermitian, we can add the 2 which differ only by having opposite helicities, and they combine to give a Hermitian pair. Same for the others. There are 4 Hermitian contributions. They correspond to the 4 quadrants seen earlier. So here we have 4 bisecting polarizations, each with opposite helicity. That is, this plane spins left and right and is consistent with this decomposition. Each of these 8 parts add up to give the singlet state. The terms that cancel are missing from the singlet state. By defining the axes in the simulation, then we are looking at the correlation from pairs like this, and not from a singlet state. The singlet is decomposed into these, and each simulated pair has more correlation due to these circled terms. It shows indeed that each pair is simulating the correlation between axes, thereby justifying a CHSH value of 3. Because of these cancellations, I conclude that the singlet state is an approximation, and it misses correlation from these terms that the simulation keeps. The missing terms all give correlation between a polarized state at Alice and a coherent state at Bob, and vice versa. This is one way to show that quantum mechanics is incomplete. It shows that entanglement in the singlet state misses correlation. To get the full correlation, we must replace the singlet with these 8 product states, and not one entangled state. To do the calculation properly, we need to work out the correlations from these 8 terms separately, and they will add up to give a CHSH value of 3, and not 2 root 2. This comes to the end of my presentation, which I hope convinces you that spin, perhaps the most important property of the microscopic, is not a point particle with 2 polarized states of up and down, but rather a structured spin with quaternion symmetry, which carries 2 complementary properties, helicity in free flight and polarization upon measurement. They epitomize the wave-particle nature, which is characteristic of quantum dimensions. I am convinced this description is correct and gives deeper insight into what exactly spin is. One reason for this optimism is that once I had the ideas, everything worked out and dropped out of the equations. All the loose ends that I knew of fit in, and I suspect others will find new insight using Q-spin. In short, it questions the foundations of our understanding of the microscopic. This can be summarized by saying that non-local entanglement is replaced by helicity, and the Dirac spin is replaced with Q-spin. Both these features come from changing the symmetry from SU2 to Q8, the quaternion group, which is afforded simply by introducing a bivector into the Dirac equation by multiplying one of the gamma matrices by the imaginary number I. Now, Q-spin is geometrically identical to that of a photon, and I find this compelling. The treatment of Q-spin finds the same correlation of minus cosine from both quantum mechanics and the treatment of Q-spin. This is an example of conservation of geometric correlation. That is because both quantum mechanics and Q-spin use the same singlet state at the source. Q-spin provides a mechanism for the separation of an EPR pair from that source. The simulation gives more correlation with a CHSH value of 1 per axis, or a CHSH value of 3 for the spin. The simulation does not use the starting point as a singlet state, but rather the 3 axes, and follows the transition of a spin 1 to a spin 1/2, or from a boson to a fermion. This is also justified by the 1/4 of coincidences being from the coherence and 3/4 from polarizations. To get the minus cosine, both Alice and Bob must both filter the coherent spins simultaneously. This leads to the rationalization of the maximum violation of the CHSH form of Bell's inequalities. Now, which is correct? The simulation has more correlation than the singlet. The simulation appears to be closer to nature than quantum mechanics, and has a CHSH value of 1 per axis, which is more than the correlation obtained from quantum mechanics. I favor the simulation because the singlet state is an approximation and misses correlation from those outer terms that we spoke of. The complementary wave-particle duality of spin acts like a boson in free flight and a fermion in a polarizing field. The formulation of this is the 2 mirror states describing the 2 axes of a spin on the same particle, rather than the matter-antimatter pair that Dirac used. Spin carries helicity as an element of reality, and quaternions exist on the S3 hypersphere. Spin extends beyond our visualization. We see only the stereographic projection onto our spacetime of the spinning or helicity observed in a spin. EPR are validated in asserting that quantum mechanics is incomplete. It is a theory of measurement, but not of nature. It does not include those higher dimensions like the hypersphere S3. It does not include anti-Hermitian attributes of nature. This gets into the foundations of quantum mechanics, with the wave-particle duality supporting Bohr's complementarity, and the simultaneous existence of both helicity and polarization on the same particle at the same time, supporting Einstein. The experimental evidence for Q-spin is the violation of Bell's inequalities and the observation of helicity. A filter could be built to separate polarization from coherence. I think this must be done to confirm the treatment here. Also, the success of quantum computing, fermionic qubits, must be abandoned in favor of free-flight bosons. The singlet state misses correlation and is an approximation. That is why quantum mechanics has a CHSH value of only 2√2 and not 3. The two mirror states are not consistent with Dirac's matter-antimatter interpretation. But for quaternion spin, there are no negative energy problems because the energies are from two counterpossessing axes on the same particle. This gives an alternate way of viewing the vacuum state and perhaps challenges the idea that the fabric of spacetime is a field of harmonic oscillators. The CHSH form of Bell's inequalities provides a quantitative measure of correlation. It defines the invisible boundary between the classical and the quantum with a CHSH value of 2. Bell's theorem is distinct from his inequalities and asserts non-locality. This conclusion was reached because Bell did not consider that other properties might exist. He only considered polarized particles of plus and minus outcomes. In this work, there are no hidden variables of any type. This formally means that Bell's work is not applicable to Q-spin and leads to non-locality as the only recourse to account for the violation of Bell's inequalities. This is challenged by defining hyper-helicity. Even so, Bell's theorem is not violated here. The CHSH value for polarizations is 2, and coherence it is 1, so neither violates the theorem. We can apply the theorem to each complementary aspect because they are distinct properties. The theorem is misleading and physically wrong. Bell did not consider complementarity. Non-locality is not needed to account for the observed violation. There are no long-range quantum channels needed. This puts into question the field of quantum information and the viability of quantum teleportation. Qubits are superpositions of two polarized states. These cannot form in free flight. Again, quantum computing should consider this. Energy is transported in free flight by the spinning due to helicity, not carried by polarized qubits. The violation of Bell's inequalities, in the end, is not evidence for non-locality, but rather evidence for the existence of hyper-helicity and other properties of nature that are responsible for local realism.